The second lab covered the motion of a falling object. It utilized my knowledge of Newton's second law and the momentum principle in order to draw conclusions about motion. The lab required me to capture a video of an object falling vertically, analyze its motion in Tracker, and create two models of the motion using VPython. I created one graph that only accounted for the gravitational force, and I created a second graph that accounted for both the gravitational force and the drag force. Then I combined the two graphs in order to determine which graph models the situation more accurately. My comparison showed that the model that accounted for both gravity and drag represented the situation the best. I recorded a video of a paper cube falling a distance of approximately 1 meter. The shape and weight of the paper cube allowed the effects of drag force to be seen in such a short time interval. After I loaded my video in Tracker and calibrated the video, I selected the center of mass of the cube for each time frame in the interval of interest. Tracker then automatically created a graph of the position versus time of the object in freefall. The Tracker graph has a few points that are obviously out of line with the overall motion of the cube. My first consideration when creating my model was Newton's second law, which is shown by this equation. With some rearrangement of the variables in the equation, I obtained a statement of the momentum principle. Both of these physics principles were the basis for my code in VPython. First, I changed the mass of the object to 0.002 kilograms. I also changed the initial position and velocity of the object to reflect the conditions of the video. In this case, I set the origin of the video to be the starting point of the cube, so the initial position is the vector 0, 0, 0. Since the cube starts from rest, the initial velocity is the vector 0, 0, 0. I chose my delta t to be 0.001. The small time steps allow for a more accurate representation of the motion of the cube, as the total time frame of the clip is only 0.533 seconds. Next, I set the j-hat value to be 0, 1, 0. This is an important part of the code because it sets the frame of reference. In this case, up is in the positive y direction. This first part is the same for both sets of code. In the first set of code that does not take the drag force into consideration, I set the b value to be 0. The while loop goes through the entire 0.533 second time interval. The net force on the cube is only the weight force, which is calculated as the mass of the cube times the force of gravity. The j-hat component creates the vector, and the negative sign indicates that it's falling in the negative y direction. I plugged this net force into my equations for velocity and position, as calculated by Newton's second law and the momentum principle. This is what the code looks like when it's run. The first change I made to the second set of code was the value of b. I used a guess and check method to obtain the proper value. I continuously ran the code with different b values until the final position nearly matched my observed final position, or negative 0.994 meters. The b value I obtained through this method was 0.002125. The net force for this code has to take into consideration both the weight and the drag force. The drag force is negative because it's working opposite the direction of the gravitational force. The standard equation for the drag force is b times the object's velocity squared. The rest of the code is the same as the previous code. This is what it looks like when the code's run. The arrow representing the weight remains constant throughout the entire fall, but the arrow representing the drag force gets larger in magnitude as the object falls. This is my graph comparing the experimental data from Tracker versus the predicted position from VPython. The predicted position on this graph does not take into consideration the effects of the drag force. This is shown in the overprediction of the final position of the cube. Without drag, the cube would fall farther in the same amount of time. This is my graph comparing the experimental data from Tracker versus the predicted position from VPython, this time including the effects of drag. The experimental data fits the predicted model much better. Here are the two graphs overlaid. When comparing the two, the effects of drag are quite obvious. The portion of the graph in the middle of the time interval does not fit the model very well. This could be due to human error when choosing the center of mass of the cube in Tracker. When examining the velocity versus time predicted by my models, I found that the model that considers drag finds the terminal velocity. I lengthened the time interval for both graphs and then ran both models. The model with only the gravitational force continues with the same velocity throughout the entire extended time interval. There is no sign of the object slowing down under this model. However, the model that includes drag shows the object reaching a terminal velocity of approximately negative 3 meters per second. If the object was thrown downward initially, the terminal velocity would remain the same for each trial. The VPython model shows that the object reaches a terminal velocity of around negative 3 meters per second no matter the initial velocity. Even when the magnitude of the initial velocity is greater than the magnitude of the terminal velocity, the object appears to slow down, as the effects of drag are the same once the additional force on the object has ended.